Yeah, welcome everyone. So let me very briefly just remind you what we did last time. We essentially spent the whole lecture proving a single theorem, which is that the space of curves, space of causal curves, CPQ from P to Q is compact. And the notes got a bit delayed, and when I put them up on the website, I realized that I forgot to put in the figures. So now I have with the figures, and today after this lecture, I'll put in a new version, which has figures for last time, as well as hopefully for this time. Now, this theorem has two important corollaries, and I'm going to save time. I'm not going to discuss them in detail here, but I must say that the proof of these corollaries is very straightforward once you accept this theorem. The theorem gave us a bit of trouble last time. Oh, I should mention that last time Wald has a discussion of limit points, limit curves, convergent points, and convergence curves. I found that the most economical way to present what he's doing is to ignore limit points and limit curves and just work with convergence points and convergence curves. The difference is that a limit point is somewhere is a point where every neighborhood contains infinitely many points or overlaps with that set. But a convergence point is when you have a sequence, and after some point, a sequence depends on some integer n that goes 1, 2, 3, 4. So after some very large n, which could be 100 or 1,000 or 1,000,000, or it doesn't matter, after that, all points of the sequence are contained in any given neighborhood. So you choose a neighborhood of a convergence point, and then the end of the sequence goes into that neighborhood. And convergent subsequence is the same thing except applied to a subsequence. So I found that using the language of convergent sequences and subsequences is enough to state and prove this theorem of causal curves being compact. And so I've redone my notes slightly to simplify compared with the presentation I gave last time. So I hope that's helpful. Okay, now to the corollaries. So there are two, there could be many, but there are two that we list. One is the causal diamond DPQ is compact. The nice thing about this is a statement about an actual subset of our full space-time. So it's a submanifold, if you like, and that makes it much easier to visualize as well as to try and prove things, because a point in this set is literally a point of space-time, while in the space of causal curves, a point is actually an entire curve, and that's a much harder thing to visualize as well as to make theorems about. But as you can guess, the way you prove a theorem like causal diamond is compact is to use the compactness of the space of causal curves and then show that every sequence of points inside DPQ converges to a point inside DPQ by putting those points in causal curves. Okay, it's an exercise, and I think it's in the notes also, in my notes. So it's very simple, so I don't need to go into it. The second one, likewise, is very nice and very useful. So the second corollary is that there is a unique geodesic of maximal proper time between P and Q. So remember, P and Q are, Q is in the causal future of P, so that P and Q have a causal diamond. That's when CPQ makes sense, that's when DPQ makes sense, and that's when this last theorem holds. So it's a time-like geodesic. Now, sometimes the question keeps coming up about whether I'm talking of time-like or null. And the problem with the null case is it raises some subtleties. And broadly speaking, I'll say that I'll get to it a little bit later. So just think of time-like P and Q being time-like separated. And there's a unique time-like geodesic that does this job. Okay. Again, the proof is straightforward using the compactness of CP. Okay, so that ends what we had to do last time. And from today, we'll talk about the behavior of geodesics. Now, an important thing is that up to now, I've actually gone through literally 3 lectures, not counting the first introductory lecture, without really mentioning geodesics. We've just not studied geodesics at all. And that's fine because we were setting the stage to discuss them, but they are the objects we really want to discuss. And I think some people might have got a little confused because when we talked about paths in all these lectures, it seemed like maybe we are talking about geodesics, but that is not what I said and also not what I meant. A path is just something you can draw. You're free to draw any path on a space-time. It need not have anything to do with the geodesic, but today we are going to talk about them. Okay, and of course, obviously, we are going to talk about them in a globally hyperbolic space-time, which, by the way, is also where all the previous statements I just reviewed are true. Okay, so compactness of CPQ, compactness of DPQ, and existence of a unique time-like geodesic of maximum proper time, all are true in a globally hyperbolic space-time. They may be true if you weaken that condition, but they're not guaranteed to be true, and our theorems apply only to this case. Okay, so what's a geodesic? So first, we are going to consider, so this section is going to follow Witten's light rays lecture in considerable detail, lecture notes. And what I'll do is start with the Euclidean case first. And then we'll go on to the Lorentzian case. And it turns out there's a little bit of non-triviality even in the Euclidean case. So what is a geodesic? So here we assume we have, by the way, Euclidean, I don't mean Euclidean Euclidean space, I mean Euclidean signature space. Okay. So geodesic by definition is something which satisfies this equation. Where x of xi of s is or t. It's sometimes a little confusing to call it t, but okay, I'll still call it t. Is a curve. We could be referring to a segment of it, and t is a special kind of parameter called an affine parameter. Okay.
Hi, Sunil.
Yeah, hi.
What do you mean by Euclidean signature case? Because I thought we were discussing globally hyperbolic.
Sorry. Yeah, good. So we are not discussing globally hyperbolic now. We are going to discuss geodesic. Okay, good. Sorry. I think yeah. Okay. I want to get to the behavior of geodesics in a globally hyperbolic space-time. But in order to get to it, we're going to make some observations in a Euclidean signature manifold, an actual Riemannian manifold with a Riemannian metric. And after we make those statements, we'll then go to a globally hyperbolic space-time and try to see what can and cannot be transported to that case from this case. It is an easier warm-up case. Okay, so I apologize. Yeah, I think going directly from this sentence to this very rightfully introduced some confusion, but I hope it's clear now. We are just doing some kind of toy example, which is not globally hyperbolic, and not a space-time either. Okay. Yeah. Okay. Good. Now, in this space, we are going to take a point and we are going to look for geodesics going away from this point. And the nice thing is that what is a geodesic conceptually is basically a tangent vector to M. So here M is our Euclidean signature Riemannian manifold, parallel transported to itself. Parallel transported. So transported parallel to itself. Now, because that's the case, you can start with any tangent vector at a given point. And since the tangent space is basically like a hyperplane, all directions are good. So there'll be a geodesic starting out in any direction that you choose from that point. And we can sort of follow it outward. There may not be a natural sense of direction, but since we are constructing it starting from a point, we can construct it in any direction. Now you can see that initially they diverge. Geodesics diverge. Well, what else can they do? They all started at a point. They can go out in any direction. So as they go a little distance, each one is further from the other one. So that's this picture depicts how, in what sense they diverge. However, and this is the interesting thing, as we follow them along the manifold, they could converge again. And I'll do an example in a second. So if they do, then okay, so we have a definition. If a family of geodesics converges, at a point, that point is said to be a focal point. Of the family. Now, of course, there's a very trivial fact, which is that I could just take this family, which I've drawn here, and put the arrows in reverse. And then it obviously shows you that I can have geodesics that converge to any point because I can have geodesics that go out from any point. But that's not very interesting. That I can always make. What's interesting is particularly interesting is if the geodesics all leave a particular point and then converge at another point. And that's a little less intuitive because obviously from this figure, you can see that if we are in the plane, then these are never going to converge. They're just going to go off to infinity, getting further and further apart. But as you surely know, there's a very nice example, and a lot of explaining of this example will depend on my ability to draw, which is not good. Okay. Oh, sorry. Well, I think I already. All right. Here's a two-sphere. And there's the North Pole, and I'm going to start there. And I'm going to have outward going geodesics. And as you know, they all converge to the South Pole, at the South Pole. So for this family, this is a focal point. Okay. Now, these are all great circles once they reach this focal point. And well, they're all equally good and they're all geodesics. They all have exactly the same length. And we also know that it's related to a symmetry of the sphere under rotation by the azimuthal angle. So far, so good. Now, the fun comes if we try to continue the geodesic past a focal point. And the interesting thing is, it may no longer minimize length. I didn't say explicitly, but it's obvious from this diagram and from the two sphere that geodesic is what minimizes length. And this is why, to the extent possible, aeroplanes follow great circles when they fly from A to B.
Sunil,
But yes.
Do you define a geodesic as something that minimizes length? Because usually
No. I
extremize
define a geodesic as something that satisfies this equation.
equal to 0.
And sorry, did I forget to write equal to 0? That was dumb. Yes, somebody should have pointed that out. So, exactly that.
So then it just extremizes.
It extremizes the length, exactly, and locally. Okay, and the point is that that's important. This is a local equation. It's just second order in this parameter. So over a short distance, so for 2 points that are extremely close, it will actually minimize length, and there's no contradiction there. The problem is that to get the distance of a finite size geodesic, you need to integrate along the curve in this parameter, the length function, and that's what it may not minimize. Okay, and in fact, it would have actually helped me to write the length function. So let's write it. It's basically I take Gij of x of t, x dot I, x dot j, then I take its square root, and then I integrate this in dt from p to q. So this is the length that we're talking about minimizing. And if q is just p plus delta p, it's very infinitesimally far from p, then there's no problem. The equation, the fact that this function, which is like a Lagrangian for a particle, is stationary, is exactly this equation here. And this is certainly going to minimize length. But it's not so clear now if I'm going to integrate all the way from P to Q, and P and Q are far apart enough to see the curvature and topology of the manifold. And now this example of the sphere helps us. So, but this time, as usual, my drawing skills will be challenged. So let's look at the sphere. But this time I'm going to draw my geodesic. So let me use a different color. And here's the geodesic. It goes from, actually, let me not call these N and S. In fact, I should never have done that. I'll call it P and P prime. So these are 2 points on my sphere. And now this geodesic is going along and coming to the South Pole. And now this is where I want to continue it past the South Pole. And I reach here, and let me call that point Q. Now you see that everywhere it's along a great circle. So it's a geodesic by definition, but it's certainly not the shortest path from P to Q. And you can see the shortest path right in front of your eyes. It's this other one, which goes in along this geodesic. Okay. But of course, that's for the two sphere, and we want some general rules. So let's try to understand how to see, given this path P, P prime Q that I've drawn, how to see the fact that there is a shorter geodesic. And the way to see that fact is that because we have a focal point, which was here, because of that focal point, the segment P, P prime admits different geodesics, or there is a segment. So focal point implies there exists a segment of this geodesic that has neighboring geodesics. In this case, it's the segment P to P prime, which has neighboring geodesics, which are other great circles that also keep going from P to P prime. So all of these are neighboring. Of course, the most neighboring, if you like, is the one infinitesimally close to this original one. Okay. The existence of the neighboring geodesics is due to the focal point. Because there's a focal point where geodesics meet, there are geodesics near my geodesic. Okay. So now there's a technique which will shorten the path for me. And let me show you the technique. First, trying to shorten the path by a small amount. And then, of course, we'll see that it can be shortened by quite a lot. Okay. So to shorten the path, our path, remember, is now from P to Q. So we do two things. One, we switch the segment PP prime to a neighboring one, to a neighboring geodesic, while leaving the rest of the geodesic untouched. Okay, so let me draw that in this color. Here's my neighboring geodesic. Oops. So you have to think of this as being a small amount away, but I'll just label this as neighboring geodesic. And this was the original one. I think that much is clear. So this process I'm going to call switching. Now, the main point about switching, so now once I switch, my new path is this followed by that. Okay, I've not changed the length because what I've done is to switch from one geodesic segment to another geodesic segment, which is of the same length. Nothing has changed in terms of length. However, something very important has happened here. And what's happened here is that I've introduced a kink. You can see, and you can try to visualize this, that while the yellow curve was perfectly smooth going from here to here to here, this curve made up of this switched segment and followed by the original segment has a kink here because, well, it's obvious because I've switched part of the curve and not switched another part. You can see the kink phenomenon just by looking at, supposing I had a situation where my geodesic was something like this, and I switch a segment from here to be like this, and maybe come to the same point. You can see that here, this original one was just going straight through that point. Straight means continue smoothly, while this other one has a bend over here. And in fact, we can associate that bend with an angle alpha, which for some purposes, I'll take to be small, which labels the deviation of the new geodesic from the old one. And now I use an intuitive fact, which is that whenever we have a kink, we can smooth it. To get a shorter path. And in this, I don't want to draw over this figure, but let's at least highlight it. If I smooth this kink, then this geodesic would come down here, but here it would sort of bypass the point P and go there. And you can clearly see that going here and bypassing P and going there is shorter than going all the way to P and going there. But now you can see, therefore, that this smoothed version is shorter than this original geodesic. Okay. And now in the sphere example, you can do better and better. instead of this red curve, you could choose this one or this one. And actually, optimally, you'll choose the curve from P to P prime going this way and come back along this. And you see, this is the worst kink you can have. It's a 180-degree kink. And when I smooth it, I just cancel out this last part and I recover the geodesic from here to here. I hope this point was clear. It's in the notes, but let me write it. For the sphere, switching to the furthest possible geodesic, which is the one diametrically opposite, from P to P prime, gives the sharpest kink. And smoothing it gives the true shortest path. Okay, but this is a luxury because the sphere is only two-dimensional. We can visualize it, we can do all this, and we can sort of check that the path is shorter. But in general, what we should always keep in mind is to smooth by going to an infinitesimally neighboring geodesic. So from this one to this one, and the way we'll think of this as being infinitesimal is that there'll be a kink angle, and I think I drew it here. Okay, here, so I'll just for convenience again label, well, this time it's a little different. We are actually switching. If we start from here, we're actually not switching the first part, we're switching the last part of the trajectory, but that doesn't really matter much. You could view it in the opposite direction. The important thing is that there's a kink angle, and we keep alpha to be infinitesimal. Now the question is, as a function of angle, kink angle alpha at lowest order, just an infinitesimal, what's the gain in length by smoothing? So in this diagram, the blue line, I should change colors. The blue line is actually I can do it exactly parallel to my sphere example. I think that will be helpful. The blue, actually, so yeah, exactly. So the blue line is the original geodesic. The red line is the geodesic to which I switched and which deviates by an angle alpha. And here's my kink. And now when I smooth it, I am going to draw something like a yellow line, which basically bypasses the kink point. Okay. And what you can see is that if all this is happening infinitesimally in a sufficiently small neighborhood of this kink point, then I can be sure that there actually is such a dotted line, which is shorter than the original geodesic, which is in blue. Okay, and the question is, how much shorter is it? So now I want to know the relation between the length of this geodesic, which was continued past a focal point, this being the focal point, and this other geodesic, which is obtained by smoothing the kink. Okay, it may not be a geodesic, but if I smooth the kink sufficiently to get an extremal line, then it will be a geodesic. But the question is, what's the difference in path length between this and that? And the claim is that we gain so the difference.
Sorry, could I ask a question?
Yeah, please do.
So in this procedure, while you're doing this, you begin with a geodesic and end with a geodesic, but in between, while smoothing, you generically don't get geodesics, right? At least for the sphere, you only have two.
Yeah. You have two geodesic segments, and it's a general rule that if I combine two geodesic segments, I don't get a geodesic. I mean, that's called triangle inequality in ordinary space. Okay. If a straight line from A to B and a straight line from B to C with an angle between them, each of them is a geodesic. The line from A to B is geodesic, B to C is geodesic, but ABC is no longer a geodesic. So as you say, what's not a geodesic in this figure is this guy. Okay. However, remember, it has the same length as what was a geodesic. That's the remarkable thing. The original thing was a geodesic. It just didn't happen to be length minimizing. This new thing, which is not a geodesic precisely because of the kink. Because if you combine geodesics with an angle between them, it's surely not going to be a geodesic. But it's the same length because this and this were geodesics. And that's because that's the fact that this is the focal point of geodesics.
Right, but I was more talking about the dashed yellow curve. Neither
yes, this one, yeah. Yes, what about it? This one?
That can't be a geodesic, right? I mean,
it can be. It gets closer to being one, and it can be in a limit. For us, the important thing is that it's shorter. Okay, once we have a direction for shortening, it can be a complicated issue to figure out how far you can go. If you like, what I've shown you is a direction for length shortening of a geodesic that was failing in its duty of being minimal length. Okay, the direction is what we just did. Now, you can try to continue doing this, or you can try to do this as much as possible. And the sphere gives you a good example. So this amount of length shortening led to a kink. The kink, if we just try to smooth out, we would go like this, which is definitely not a geodesic, because it's still true on the sphere that every geodesic better be a great circle. The problem is every segment of a great circle need not be the shortest length geodesic. And that is the problem we started with, that P prime Q like this was not shortest length. But this other thing done by smoothing a kink is also not, it's not geodesic, but it's better, it's shorter length. So we've improved, we've shortened the length. Now in the circle case, what I can do is to choose my geodesic, this segment, to be deformed not to this red one, but to one which is here. I can deform this to its diametrically opposite cousin, and then have the kink here. And now in this case, which is very finite, it's not an infinitesimal deformation of the original P prime. In this case, I can go here and come back here, and this is a huge kink. And if I smooth this kink, it just amounts to dropping this part altogether, which was just going from here and coming back and just staying here. So when I go from P to Q, I just stop at Q. That's a geodesic. But we are not addressing here the question, when can you get a geodesic by this means? So thank you for highlighting that. That's a different question. And that will not be something we can do in a manifold independent way.
Sorry, about this last comment. So are you saying that given a focal point, there's no guarantee that you will end up in a shorter?
No, there is a guarantee that I'll end up in a shorter path. I've just shown you how to end up in a shorter path. Now, whether that shorter path is the shortest path between those 2 points is what I'm not guaranteeing. In general, it's not actually, because most of the time we are going to study infinitesimal deformations of the original geodesic, which was not shortest. So by smoothing the kink, I've only shortened the path. That's all. That I'm showing a proof of existence of a way to shorten a path. This is not, it doesn't tell you any construction how to keep shortening the path, but it tells you that whatever path you had was not the shortest one. And here's a better one.
I see. Thanks.
Yeah.
Hello. Can I ask? Yeah, the procedure seems slightly ad hoc, because what would you do if I would just wound around the sphere multiple times and end up somewhere? Like it crosses the original point and the focal point multiple times. So
yes,
what do you expect to be done?
No, I can still as long as I'm passing through a focal point, I can still deform to a nearby geodesic, and I can still smooth kinks to shorten the path.
Sure.
Yeah, yeah.
But this procedure is not quite terminating in that sense. What would you do if I just wound around
the procedure? Yeah, so you can have many geodesics that wind around the sphere as well as geodesics that don't. So there are global issues. Okay, how to put it? Um, uh, as I said, I think the statement I've made is correct. I think what you're saying is that it's not a way to construct a shortest possible path among all geodesics. That may be true.
Yeah.
It's really a way to shorten a given geodesic.
Okay.
Yeah, so exactly. So I think everyone here in the chat I see wants to be very ambitious and go to something much more ideal, which is given a geodesic, find the shortest geodesic. Actually, in a way, that's not even a very sensible question, because if you want to find the shortest geodesic, you should just start by finding the shortest geodesic. If you know how to find geodesics, just do it. Why do you need to be given a geodesic that wasn't shortest and then use it to find the shortest one? You don't need to be given anything, just given the manifold, find the shortest geodesic between P and Q. So well-posed problem, but it's not a very practical problem. The practical problem is, given a geodesic that doesn't that passes through a focal point, there's a method to shorten the total length of the continued geodesic if it continues past a focal point. And this gives a sort of significance to the focal point. First of all, tells you that the focal point is a place where the shortest length nature of the geodesic just doesn't hold after that. Okay, it was holding fine till you reached a focal point, and then it stopped going. Yeah, smoothing indeed means we are going to bypass the intermediate point, Vivek, thanks. And that's exactly the point of it. This is the intermediate point in this local diagram. And it's not important because our geodesic is from here to here. We're trying to go from a point P to a point Q, and we just happen to pass through a focal point, but we are not trying to pass through a focal point. We are trying to get to Q from P. Okay. So good. Thanks for all the good questions. Now the question is difference in length. Length of the new path versus the old path, which was a geodesic. For infinitesimal kink angle, is of order alpha squared. I think you can readily accept this. A geodesic is extremizing something. Okay, so if I deviate from a geodesic, the fact that it's extremizing length means that to first order, its length doesn't change. Okay, so generically, the first time you see a change in length is at second order. Is that okay? So that's a key fact. Okay. I'll refer to this phenomenon as this whole phenomenon I've discussed as the shortening phenomenon. And I'll emphasize that it was made up of two steps, which I'll try to highlight here. One was to switch using the existence of a nearby geodesic on a segment. Okay, so the nearby geodesic on a segment in the sphere case was the PP prime in yellow versus the PP prime in red. And here similarly, it's the original, it's basically this versus this. Switch is the first step in the shortening, but switch does not lead to any gain in length or any change in length. It's simply the same length, but after introducing a kink, having introduced a kink. Now, once you can switch, you can also do the second thing, which I'm calling smooth. So switch and smooth is the kind of, if you like, the slogan. Switch to to a new geodesic, which you found thanks to a focal point, smooth the kink, and you've reduced your length, and you've reduced it by second order relative to the angle that the kink introduced, which is of the order of the switch. It basically parameterizes how far you went from your original geodesic to the neighboring one. Okay. Now, there's a very interesting and subtle point, which is that this procedure amazingly works. This procedure can work even if the segment to which we switch is not a geodesic. But under special conditions on that segment. So here it's the segment in red. This is the new segment that I found because this was a focal point of geodesics. So both these red things, both these things I'm highlighting now are geodesics. But the statement is that if this was not a geodesic, it would still work if the second segment satisfies a certain property. It works if the new segment satisfies the geodesic equation up to and including first order in alpha. Okay, so there's a parameter alpha, and if my new segment satisfies the geodesic equation exactly, then it's a geodesic. If it fails to satisfy, but it still does satisfy to zeroth order and first order in alpha, and the failure is from second order. Okay, then things are good. So then, and it fails in second order. Then what happens is that the change in length, there'll be a change in length for failing to satisfy the geodesic equation, but this change in length will be of order higher than alpha squared, namely order alpha cubed. Okay, so in this case, what's happening is that I'm allowing a change in length, but of this segment. This is before smoothing. Okay, so I'm choosing such a segment that its change in length relative to this one is of order alpha cubed, not alpha squared. Normally the change is of order alpha squared, but now I'm assuming that this thing is approximately a geodesic up to and including first order in the deviation. So its change in length is of order alpha cubed. Okay, in that case, after I smooth, this new thing is going to again have a change in length of order alpha squared. Now, when alpha is infinitesimal, these two effects cannot compete, and the alpha squared order change in length due to smoothing will still win, and I'll still be able to reduce the length. Okay. So then this cannot compete against the effect of smoothing. Order alpha squared. So shortening still takes place. Still holds. It's a subtle difference, but I understand that is going to be important. And so I'm just putting it out there. Even if you don't want to think about what kind of equation it satisfies, all you have to think is that this new curve, which I'm switching from this old one, instead of being a geodesic, can have the same length as the old one plus an error of order alpha squared. That's allowed. Sorry, error of order alpha cubed. Where that error comes from is the fact that it satisfies the geodesic equation with error of order alpha squared. Witten has a footnote in which he explains this purely in terms of functions. So if this wasn't clear, you can try to follow that. Okay. Can I explain why it's alpha squared? It will still have to pass through the focal. Sorry. No, I didn't understand your question, Sambit. Why it is alpha? What is it? There have been many alpha squareds on this page. Tell me which one you're referring to. Sambit?
Yeah, sorry, those are two separate questions actually. I just asked initially if you could explain why it was alpha square, and the other question was.
No, please, one question at a time. What is it which is alpha squared? I still didn't understand your question.
Yeah, you wrote that. So you wrote that it would be alpha square, right? Again, I'm using it. Sorry. Wait a second.
Take your time, but tell me what is it that you want explained, please. And only this question, then we'll go to the next one.
You wrote that the difference in length of new path versus the old path.
I can't hear you. Your voice is disappearing. Please speak into the mic.
Can you hear me now?
Yes.
Okay, so you wrote that the difference in length of new path versus the old path for infinitesimal kink angle alpha is of order alpha square.
Yes.
Yes, that line.
Oh, thank you. So the reasoning for that is that good. This sentence, I think, is what you mean.
Yes.
The reasoning is that the length of this path is stationary by definition of geodesic. Okay, that means that if I take a geodesic and deviate from it by an infinitesimal amount, even this amount, the length doesn't change to first order. That's what stationary means.
Right, okay.
That's the reason why it's order alpha squared. It's the same reason why in field theory, if we expand around something, the expansion is always of order second order in the expansion. If we expand around the background, the first order in the expansion vanishes by equation of motion and we get the second order. And the geodesic equation is actually the equation of motion of the Lagrangian that I wrote for you. Since it solves that equation of motion, any deviation to first order will not change the length to first order.
Okay, got it.
Yeah. Now, the second question is if I'm considering the non-geodesic second path, right, to which I switch?
Yes.
Yeah. So the problem then is that there isn't a focal point. A focal point by definition is a point where geodesics meet. But in the second case, when I'm allowing to switch from a geodesic to a non-geodesic, this thing isn't a focal point because it's only a point where a geodesic and another curve that isn't a geodesic meet, and there's no big deal in such a thing. You could have called it an approximate focal point, but nobody uses that terminology, and it's not a good one for the reason that it's not that two geodesics miss each other slightly, and that's why it's an approximate focal point. Here, it's approximate because one of them is an approximate geodesic.
But then how would you define alpha for that? I mean, you're defining alpha in terms of
I'm picking a point. First, I've got this geodesic. I pick a point on it from where, by some miracle, which is not based on focal points, I happen to know about the existence of another curve, which is approximately geodesic and leads me to the same place.
Okay,
it's up to me to pick this point now. This is why, as Witten also puts it, focal point is not necessarily the main criterion here.
Okay.
Focal point would be the criterion. The focal point would be the unique place for me to switch to another geodesic, because by definition, that's where the two geodesics meet. But if I have a point where I feel like switching to another path, I can just do that, but I have no right to call that point a focal point if the other path isn't a geodesic.
I see.
Okay. Okay, so this is the subtle point, and shortening still holds. Please feel free to ask me next time or in the on the blog page if it's not clear, but after going through it once. So try to think about this order alpha squared business.
Can I ask a question?
Now, yes, please.
Focal points. This might be relevant, so please feel free to postpone it.
Yeah.
Given a point on the manifold, do you have a unique focal point, or can there be multiple
No.
focal points?
Yeah, we don't know. There could be any number.
I see.
We know not.
Do you know
In
of
principle, well, for the sphere, there are infinitely many focal points. It all depends where you start, right? Actually, in fact, almost there's a trivial answer. Every point of the manifold is a focal point of some geodesics, because I mentioned this in the beginning. It's the point where all the geodesics going out from that point come back and meet.
I understand. So I'm giving you the beginning point. I'm giving you a point and then asking.
Good. Then it depends very much on the manifold, and you can't make a general rule, I believe.
But do you know of a simple two-dimensional, for example, example for which there's multiple focal points? I mean,
I don't know for a fact, but I would, if I had to look for an example, I would look for a genus G Riemann surface.
I see.
And start somewhere, and you see they have so many handles and stuff that your geodesics can go around this way, around that way, and they could meet at the other end. Maybe, I don't know. I don't know if anyone else here knows, but you're welcome to look it up or put comments in the chat.
Thank you.
I don't know. Ashok is here. If you know, I don't know if he's here. He's certainly signed on. Ashok, do you know? Are you there? And do you know?
Yeah, I mean, I don't immediately recall, but I don't also know of a reason why it shouldn't be there.
Thanks. That's exactly the right statement. There's no reason why it shouldn't happen. And in fact, look at the sphere also. Anyway, the sphere is very special, and I think we shouldn't set too much store by that. We simply allow for it, and if it's not possible, then yeah. Now on a torus, torus is an interesting case for various reasons, and one of them is a case that somebody brought up earlier, which is that you could have geodesics winding around it many times. But on a torus, it seems you could have two. Okay, I don't have time to think through. Let's move on, and let's talk about these things in the blog. Okay, good. Now, last point to discuss this has been a long discussion of Euclidean manifolds, but fortunately, the discussion is a little bit simpler and also a little bit more complicated in the Lorentzian case. And I want to certainly do that today, because once we are done with geodesics, then next time is Raychaudhuri equations. Okay. So here there's another interesting case when we consider geodesics from P, not to another point Q, but to a submanifold S of the manifold M. I'm still in the Euclidean case, but I'm still using the familiar symbols S and M. So here's my big manifold. Here's my point P, and here is some submanifold S. And instead of defining a geodesic from P to Q, where Q is given, I define the geodesic from P to S, where S is a manifold. And that actually means, as you can imagine, that I start from P and I send out paths, and I scan only the subset of paths which intersect orthogonally this manifold. That's well defined because I can take the dot product of the tangent vector to the manifold at that point and the tangent vector to the curve at that point, and I can take the dot product in the given metric G mu nu or Gij in this case, and that's, if that's zero, that's orthogonal. This even works for the Lorentzian case. Just G mu nu, the dot product of tangent vectors, should be 90 degrees. The reason why we only scan among these is that any other intersection angle immediately allows you to shorten the curve by moving the point on the manifold. Has to be pi by 2. Otherwise, so we have a new freedom here, which is to move the point on the manifold. So let's take this point Q. By moving it until it reaches a point where this intersection angle is 90 degrees. Okay. But now the definition of focal point is different, because now what could happen is that I have a point here called P prime, from where there's a geodesic that intersects the manifold at right angles and has the same length as the previous one, but doesn't hit the manifold at the same point. It hits the manifold at another point. We think of the manifold as a potential landing place, and we're always supposed to land vertically. Okay, so this leads to a new definition of focal point. Where two different geodesics to them 2S meet. Okay, and now the switching phenomenon is pretty much the same. Okay, I can again do everything exactly as before. It's just that this thing, which I call a focal point, wouldn't have been called a focal point if I had fixed the destination point to be Q, because the new thing P prime Q prime doesn't even land on Q. But my requirement now is not to land on Q, but to land on S orthogonally. That's a more general requirement. But everything goes through the same as before. So you take this path, you switch to this neighboring path, you introduce a kink over here, you smooth out the kink, and you have a shorter path. Okay. And actually in this drawing, it looks to me that the shorter path at the very end of the process may not actually intersect the manifold at 90 degrees. I think that's correct. You can correct me if I'm wrong. So again, all we've done is to shorten the length by doing this switching and smoothing, but we haven't made any claim that the new shorter length corresponds to a geodesic. Okay, so that's all I have to say, and all that's in my notes as far as the Euclidean case is concerned. And now it's really interesting to get to the Lorentzian case. And here things are different in very interesting ways. And let's see how much we can do. Okay, first of all, the geodesic now is this. Equation is now this. It's the same equation, really. Okay. But now the point is that the affine parameter, so the parameter, now I won't call it S. I won't call it T, I'll call it S. So x dot mu means dx mu by ds. Okay. And now there are different things you can choose this to be, depending on where you are, on where what your tangent vector is at a given point. So the curve. Okay. So first thing to establish is that yeah. So locally, a curve can be space-like or time-like or null. I'll mention here, though, that in a moment when we go to geodesics, we will see that the geodesic is either entirely space-like or entirely time-like or entirely null. It can't move between these things. But a general curve can be. And so the parameter for a curve, the parameter S, it's an affine parameter, but it has a natural choice in at least two of these cases. So we can choose it to be the proper distance for the space-like case. We can choose it to be the proper time for the time-like case. And for the null case, we have to choose it arbitrarily as an affine parameter. Affine parameter is a parameter in which this equation is satisfied, and then changes of this parameter by a linear transformation will keep the equation satisfied. So it's in some sense arbitrary affine parameter. It can be given a physical meaning by relating it to a physical situation, but just in pure geometry, there's no natural thing because the proper time and proper distance in the null case are just 0. Okay. Now, one interesting fact is that, okay, now what is the length? So the length of a path now, I should have actually given you this before saying the previous things, is defined to be L equals integral ds square root g mu nu x dot nu for the space-like case. It's equal to the same thing, but with a minus for the time-like case. And is just equal to 0 for the null case. Okay. Now, sometimes authors like to put a mod sign under the square root. That would make the first two lines formally the same, but it's a little misleading because, as I told you, a general curve, not a geodesic, can have space-like and time-like and null segments to it. And it doesn't really make any sense adding up the length over all those segments. Okay, so Wald actually, who is more careful than most people about these things, points out that generic paths in space-time, there is no well-defined concept of length. So we can call these all length, but there's no well-defined concept of L for a generic path which has segments of all kinds, space-like, time-like, and null. However, for geodesics, now, what is special about geodesics? They involve parallel transport of the tangent vector. They are actually created by the equation. Geodesic equation is the same as parallel transport of tangent vector. And that preserves the norm of the tangent vector, which is exactly x dot mu. And so that norm, if I choose it at the beginning of the geodesic, if I choose that norm to be a space-like norm, then the geodesic is space-like. If I choose it time-like, the geodesic is time-like. If I choose it null, the geodesic is null. So this implies that a geodesic is everywhere time-like or everywhere space-like or everywhere null. And then the length of the geodesic in this sense, this invariant length or interval is well defined. Okay. Now we can ask the question, what can be said about lengths of geodesics? In space-time. Lengths as defined above of geodesics in space-time. Well, one of them is obviously trivial. If it's null, the length is 0, and that's the end of that. Okay. But if it's space-like, it turns out that there's no bound to the length, neither lower nor upper. And the way we see that is the following. Imagine that the geodesic connects a point P to a point Q, which I've drawn at a space-like separation. Okay. So, of course, you might think that, okay, let's do Minkowski. Let's first do Minkowski, where we can draw things. Now in Minkowski, the affine connection is 0 in the rectilinear coordinates x, y, z, and t. So the geodesic equation is just x double dot equal mu equals 0. So it's a straight line. So I can just join P and Q by a straight line. So geodesic, it's a space-like geodesic. It has a finite length, but it's not neither the minimum nor the maximum length that you can have. And the way you can change this length is the following. First of all, let's reduce the length. To reduce, we take this, and what we do is we go. So I'm going to draw curves at exactly 45 degrees, which look null. Well, exactly 45 degrees is not something my drawing skills can accommodate, but I think you get the point. Okay. Now, this is like a null trajectory from P to Q, but actually we want it to be space-like, and we can easily do that by just being under it, under and over. I don't know if you get my point, but smoothing it out, we get a wiggly trajectory like that, which can be arbitrarily close to this sawtooth thing. Okay. Now, what's the length of this yellow curve that I've drawn? It's exactly 0, because every segment of it is null. So its total length is 0. Okay. Now, if I smooth it out, obviously it will not be 0, but I can pick any epsilon, a small parameter, and smooth it out in a way that it's always space-like. This is a very important thing. You'll see that it's always space-like. And as long as it's space-like, it's legitimate. And as long as epsilon is small, it's as close as I want to this jagged thing. So therefore, the conclusion is possible to reduce to 0. Okay, is this point clear? Space-like path can always be reduced to 0 length. Okay, I can also increase it. And how do I increase it? Well, I have all of space available to me, remember. So let me draw the plane. So here always we have, this is space and that's time. That's x, y, z. So I take a path from here. Now I'm not talking of geodesics. I'm simply saying there's a path that can reduce the length of this straight line, and it can increase the length also. The one that reduces is this null, everywhere null path. And the one that increases it is to basically start from P and go around for a few days and then end up in space and then end up at Q. Okay. Obviously, I've drawn it a little carelessly, but I think you can see the point, which is that we have all of space to wander in. So maximizing a space-like path is no big deal. It's just like maximizing a path from A to B in just 3D space. Okay, and obviously you can do that. You can't minimize a path in 3D space beyond the straight line or the geodesic, but in space-time, you can make use of the time direction to minimize the path by doing these null trajectories. So the conclusion is that, let me get rid of these things that I added. Okay. The conclusion is that I can increase it to infinity. So there's nothing interesting. This is a generic, this is for Minkowski. With a little effort, you can see that I can do the same thing in bits and pieces over any manifold. So I have a path from P to Q. I can construct my little light cone. I can go nearly as fast as speed of light, come back, go again, come back again, and so on. And I'll reach from P to Q in the shortest possible time. By the way, this fact of the existence of a nearly null path from P to Q is exactly okay, not for the space-like case. We'll come to the time-like case. Okay, so so good. So our conclusion is that there's nothing interesting that you can study about the length of geodesics in space-like geodesics, because paths can be as long and as short as you want. So there's no bound that they're going to ever saturate. Okay, null is also likewise not interesting, at least at this stage, and that leaves us time-like. And now time-like, so here's P and here's Q. You can still go from P to Q by something that's approximately null, but now it's epsilon towards the time-like direction. You can still do the construction I did, or if you really want, you can do an even simpler thing. Just go exactly at 45 degrees this way, and then at 45 degrees the other way, and you're at Q. And the whole thing is 0. So what's it called? The proper time is 0 for this path. And again, to be time-like, we just need to stick inside it. So like that. Okay, then we are always everywhere time-like. And we've taken 0 time. And as many authors have pointed out, I'm not sure who was the first in this context, but this is the twin paradox. Because the for the twin paradox, a convenient thing is to take Q just above P. That means the one of the twins doesn't go anywhere and just sits at home. The other twin, however, travels along at nearly the speed of light, reaches somewhere, and then travels back at again nearly the speed of light in the reverse direction. And the second twin, who traveled, has traversed almost no proper time. So actual path is something like that. And so depending how close that person can get to the speed of light, they've traversed as low, a small amount of proper time as you like, while this person has been sitting here all the time and has aged at the normal rate. So this is twin paradox. Okay. And the conclusion from this is that we can shorten the proper time, but now we come to the maximum proper time. And in Minkowski, that is actually the straight line. So in Minkowski, there's no way to increase the proper time for a time-like path between P and Q. If P and Q are like this, Q vertically above P, then we are at start and end at the same space point. But I could also have chosen Q here. Wouldn't really have spoiled anything much. I would have had a straight line path from P to Q, and that would be the maximum one. You might wonder why I can't do the zigzag thing which I did in space. Well, you see, in space, I can roam around space by going, let's say, in a circle, XY plane. Okay. As far as the time direction is concerned, I'm not moving in that direction. So my vector when I'm doing a circle in space is always space-like. But the time direction, there's only one. So if I'm going up in time, and if I want to wiggle around, that's fine. But I can't do this, because every segment when I'm coming down would be going back in time. And that, even if I allow that, the part where I change from going forward to going back in time, that part is space-like. So that's what I'm not allowed. Okay. So the conclusion is that there is a maximum proper time. And actually, we proved some theorem at the beginning of this class about maximizing proper time, namely in a globally hyperbolic space-time in general. There's a unique geodesic that maximizes proper time, and this is the place to put it in context, because in Minkowski, it's the straight line, but in a generic manifold, it's difficult to say that it exists a priori or to draw it, but the theorem following from compactness of the space of curves from P to Q actually guarantees me that there's a unique geodesic of maximum proper time. So this works very nicely. Okay. And now, are there any questions on this? Then it will only take me 5 minutes to consider the focal point story. Okay. First of all, I'm not going to write this, but okay, before I get to that. First of all, yeah, so now we ask the question, focusing. What is focusing? Well, it's the same as before. Geodesics meet. At a point. Yeah, focusing, I think in general, we should say geodesics starting at a point, meet at another point, and they're time-like, so I should draw them this way. And this is, I'm imagining now a general globally hyperbolic space-time, and two geodesics are meeting at a point. And the question now is, what can I say about the length, path length, or proper time of a geodesic, one of them, let's say, that continues beyond that meeting point. So to keep my notation, this is P prime, the focal point, and this will continue to Q. Okay. So now the story is quite similar. I basically take, except I've forgotten the colors I used, but I think I can do it. So the first curve is the one that I was using to define a geodesic, past a focal point and went to Q. The problem now is that not that it's no longer minimum, as in the Euclidean case, now it's no longer maximum length. It's the exact opposite. Okay, because time-like geodesics maximize the proper time, this curve P prime Q, this one, no longer will maximize the proper time. And to see that, we use the fact that because there was a focal point, I can switch to this guy. And once I do that, then there's a kink. And once I smooth the kink, I now have this sort of curve, which bypasses the focal point, and it's longer than the previous one. Okay. Now, why is it longer? I think it's almost obvious from my diagram, because if you see these segments, okay, not so obvious from my diagram. Is it obvious from my diagram? Okay, so the claim is that the triangle inequality works in this way, that if I have three time-like paths, P to P prime to Q, and the direct path, then this one has a longer proper time than these two. But at this precise moment, I'm not finding a diagram that will exactly show me that. Are people convinced? Then I can just state it.
I think one of the segment looks more space-like. That may be the reason.
Yeah, that's the problem. I agree. When you start with a bad diagram, you run into trouble. Let's try again. So we have P, we have Q. We don't let anything look too space-like. And we have this, and this, and this, and the shortened path. Yeah. So hopefully what you can, actually the best way to see it is this sawtooth construction, which works in both cases. The point is that the more jagged path actually has more time-like segments that cancel, has more movement in time that cancels from your proper time, and therefore, has more movement in space, excuse me, that cancels from your proper time. And so it's actually shorter. That's right.
Yeah, it may be easier to draw Q just vertically above P, right?
Okay, let's try that. Yeah, a lot of people draw Q above P. I always used to think that's a bit cheating, but I think that's probably okay. That's probably okay.
I think you can always do it, right? If a time-like separated.
Yeah, I guess you can always do it by going into by suitable boost, say, if you're in Minkowski. Yeah. So this and then this, and finally this. Anyway, let me just write the conclusion. So smoothing, switching works just as before. We go from the original segment to a new segment. Introducing a kink. Then smoothing also sort of works as before, but it maximizes the length. And so, yeah, so I keep dodging between arbitrary manifold and Minkowski. I think here I'm actually talking of an arbitrary manifold. And arbitrary manifold with a focal point. So the focal point, so I'm given that there's a focal point. So it's arbitrary, but I'm assuming there is, yeah, isn't the maximizing just because of the minus sign? Of course it is. It is, that's fine. And that's correct. That's basically correct. So, but the important thing is that the phenomenon is the same. So what is really nice is that all the techniques we introduced for the Euclidean signature case basically work as long as we go through a little bit of pain in the beginning to point out that there's nothing to discuss for the null case, there's nothing to discuss for the space-like case, and the time-like case basically works by this story of proper time, and we can and there's a maximum proper time. And when you pass a focal point, the proper time that your geodesic is taking may not turn out to be the maximal one to the place where you want to get. And that's the key result. And that's actually all I want to say today. So we have actually finished well on time. You can add this little story of geodesics from a point to a submanifold rather than a point to another point. And that will be relevant, but it's the same discussion, okay? Again, geodesics to a submanifold should hit the submanifold at 90 degrees. And a focal point will be one where there's a new geodesic also hitting the submanifold at 90 degrees, but possibly somewhere else. Okay, so this sort, and oh yeah, and approximate geodesics also works exactly the same way. If I flip from a geodesic to something that's nearly a geodesic, but not quite, but it solves the geodesic equation up to and including first order, then also I can switch and I'll still increase my proper time. So all these points, I believe, are going to be relevant in what follows. And details, well, I have typed all this in my notes, which I'll be putting up soon today. And Witten's notes have more detail. And by the way, one comment I forgot to make. Geodesics, if you feel you'd like to understand geodesics, like the very basics of geodesics from scratch, please look at Wald's book, chapter, I think it's 3. That is a nice one description in the sort of mathematical spirit that we are using here. And I thought I had written that in my notes, but apparently not. Okay. But please do look up that because it's quite illuminating. Okay, questions, comments?
Okay, so I mean, why are we interested in minimizing the lengths of geodesics? I mean, particles follow geodesics, and that's it, right? Why would you want to study?
Well, I could give a flippant answer. I mean, if you've ever been on a train, you would definitely want to minimize the proper time. So but or minimize the distance. If you have to travel somewhere, you want to minimize the distance. But I think a more serious answer is that often the dominant contribution to a physical process comes from a physical process can take place due to various competing effects. So for example, I can reach a place following various different paths. And sometimes, and we'll see that in the next couple of lectures, you can learn something about the geometry of a space-time by just knowing what its geodesics are doing, or what its shortest, what its extremal paths are doing. So yeah, null case, Sanket, thank you. Null case we will come to. Null case needs separate treatment. And so Witten took an interesting approach, although Penrose's singularity theorem, which talks about formation of black holes, was the original result, and Hawking then used it to talk about cosmological singularities. It turns out, for obvious reasons, that in cosmological singularities, you only need to know about the behavior of time-like geodesics. So everything we have done now will apply to the cosmological case, and that's what we'll come to after discussing Einstein equations and Raychaudhuri equations. And Penrose's singularity theorem will come later. That does make use of null geodesics, so we'll have a separate discussion on null geodesics at that time. But coming back to the earlier question, why are we interested? I think it's not that we are interested just in the trajectory of one particle. We are interested in generic families of trajectories. And as I said, we are interested in showing that space-times actually have singularities. And we are trying, I think the idea is to, in some sense, blame the singularity or to highlight the singularity or pinpoint the existence of singularity based on what geodesics are doing. And then if the geodesic fails to be of maximum proper time, then it will give us some different physical result. Let's wait for that.
Okay, could I just follow up?
Please.
Okay, so I mean, if your objection is that we want to study if a clump of particles starting at a point will converge or diverge, then I would be interested only in the focal point or the properties of the focal point, right? Why would I want to maximize or minimize the length of the geodesic itself? I'm probably
let's wait and see.
Okay.
So near the end of time now, and it's going to come very soon. One thing we haven't done yet, by the way, is to use Einstein's equations at all, really. So we'll have to first, we'll have to talk about what happens in GR, what is the evolution of a space-time in time, which is the process of cosmology, but it's also the process of black hole formation. And at that time, we'll understand precisely what we want, why we want to know all this. Okay, I think we're done. Thank you all very much. Wonderful audience as always. See you on Friday. Why we are after maximizing proper time instead of minimizing? Thank you, Sahil. The answer is that minimizing takes us to zero. So there's nothing you can, there's nothing interesting there, right? Maximizing is non-trivial. The precise statement is that we don't know what is the maximum proper time between P and Q on a generic manifold. Okay. And in order to know it, or in order to find a curve that takes the largest possible proper time, we need to study focal points and so on. But for the minimum proper time, it's just zero. We just keep going at the speed of light, and our minimum proper time to any place is very small.
Thanks, Sunil.
Thank you all. Thanks. Bye.